Hello, friends. Welcome back to Sign Up Sarah. Let's dive into a very interesting question. How does a flock of birds find food without a leader telling them where to go? No maps, no GPS, no one in charge. Yet somehow the whole flock converges on the right answer fast. This is particle swarm optimization, a search algorithm that copies exactly that behavior, and it's one of the most elegant ideas in all of computer science. Imagine an island. Some parts are rich with food, some are barren. Your job is to find the richest spot, but the island is huge and you can't see the whole thing at once. You send out a flock of birds to search. Each bird lands somewhere random. That's your starting population, your swarm. The birds start hopping around, exploring nearby areas. Here's the first key rule: each bird remembers the best spot it has personally ever visited. That memory is called its personal best, or P best. Those little flags you see, each one marks where a bird has found the most food so far. Now, here's where it gets interesting. The birds talk to each other, they compare notes. Whichever bird has found the single best spot in the entire flock broadcasts that location to everyone. That shared record is called the global best, or G best. Every bird now knows where the richest food has been found so far. So when a bird decides where to fly next, three things are pulling at it simultaneously. First, inertia. It keeps moving in roughly the direction it was already going. Momentum. It doesn't just stop dead. Second, cognitive pull. Its own best memory tugs it back. Something like, hey, that spot I found 3 hops ago was really good. Maybe I should head back that way. Third, social pull. The global best attracts it. Something like, the rest of the flock found something incredible over there. I should check it out. The actual movement is the sum of all three. That tension between exploration and memory and social influence is the entire algorithm. Let's translate the bird story into mathematics. Each bird becomes a particle, indexed I. Its location on the island is its position vector x sub I. The direction it's flying is its velocity vector v sub I. Its personal memory is p best sub I. The flock's shared record is g best. And the velocity update equation, the single line of math that drives everything, looks like this. V new equals W times V plus C1R1 times P best minus X plus C2R2 times G best minus X. Three terms: inertia, memory, social influence. That's the whole algorithm. Let's watch it run for real. The swarm starts scattered randomly across the landscape. Watch what happens over just a few dozen iterations. The birds aren't following a script. No one told particle 4 to go left, but the collective behavior drives them toward the peak. The richest food source? This is emergent intelligence. Simple local rules producing globally optimal behavior. So then, what is particle swarm optimization? It's a population-based search algorithm inspired by the social dynamics of flocking. Each agent explores the search space guided by two things: its own best experience and the swarm's collective knowledge. No gradients, no calculus, just memory and gossip, scaled up to thousands of dimensions. So let's dive into the algorithm. Before we can understand how particle swarm optimization works, we need to understand what problem it's actually solving. This is an objective function, a mathematical landscape. Every point on this surface represents a candidate solution. The height at each point tells you how good or how bad that solution is. Your job is simple to state and brutally hard to solve. Find the lowest point. Now, on a smooth bowl-shaped surface, that's easy. Roll downhill, you'll get there, but this is not a smooth bowl. This surface has local minima, valleys that look like the bottom, but aren't. If you use a standard gradient-based method, just follow the slope downhill. You'll fall into one of these traps and stop. You'll think you found the answer. You haven't. This is the fundamental problem in optimization. Not just find something good. Find the global minimum, the actual best solution in a landscape designed to fool you. There it is. The true global minimum, hidden among dozens of imposters. A classical optimizer, start from the wrong place, will never reach it. It'll get stuck in whichever valley it falls into first. Let's look at this from above. The contour lines you're seeing now are like the elevation lines on a hiking map. Each ring represents a constant value of the function. The closer the rings, the steeper the slope. The gold dot at the center, that's still our target, the global minimum. Here's the question that motivates everything that follows. How do we find this point without already knowing where it is? We can't just look at the map and point. In a real optimization problem, you don't get to see the full landscape. So we have a landscape full of traps, local minima everywhere. Classical methods get stuck. Here's the PSO answer. Don't send one searcher, send a swarm. Let's zoom in on a single particle, one agent in that swarm. It has a current position on the landscape. It has a history, the best place it's personally ever been, marked here. And it knows the swarm's collective record, the single best position any particle has found so far, marked with the gold star. 3 pieces of information. That's everything this particle knows. The first force shaping its next move, inertia. Whatever direction it was already traveling, it keeps going that way. Not indefinitely, but with some weight. This is what stops the swarm from immediately collapsing on the first good spot it finds. Inertia keeps the exploration alive. The second force, cognitive pull. The particle remembers its personal best position, that cross marker, and it feels a pull back toward it. I found something good over there. Maybe I should head back. This is individual memory. Every particle has its own, independent of the rest of the swarm. The third force, social pull. The gold star, the global best, attracts every particle, not just this one. Every single agent in the swarm is being pulled toward wherever the swarm collectively found its best result. This is the gossip mechanism. Good news travels fast. These 3 forces don't fight each other. They add tip to tail, inertia, then cognitive, then social. The resultant is the new velocity vector. That green arrow is where this particle is headed next. The balance between these 3 forces is what makes PSO tick. Too much inertia and the swarm explores forever, but never commits. Too much social pull and everyone collapses on the first good spot, ignoring better options elsewhere. Let's now write it out as actual mathematics. We've seen the intuition. 3 forces, 1 particle, emergent behavior. Now let's write it down precisely. Because the power of PSO is that this intuition translates into a single, elegant equation. The velocity of particle I at the next time step. That's what we're computing. Everything on the right is what determines it. The first term, W times psi v sub IT. This is inertia. The particle's current velocity scaled by a weight W, typically between 0 and 1. If we're close to 1 means the particle carries a lot of momentum. It keeps moving in roughly the direction it was already heading. If I'm close to 0 means the particle is more willing to change course immediately. This single parameter controls how much the swarm explores versus exploits. Too high, the particles fly past good solutions. Too low, the swarm stops searching and collapses prematurely. The second term, C1R1 times the difference between the particle's personal best and its current position. This is the cognitive component, the memory pull. Notice the structure, P best minus X. That's a vector pointing from where you are to the best place you've personally ever been. Scale it by C1, a constant around 1.5. Then multiply by R1, a random number drawn fresh every iteration, uniformly between 0 and 1. That randomness is deliberate. It stops the cognitive force from always pulling with the same strength. It introduces stochasticity that keeps the search from being too deterministic. The third term, C2R2 times the difference between the global best and current position. Same structure as cognitive, but this time pointing toward the swarm's collective record. C2 controls how strongly social influence pulls relative to personal memory. R2 is another independent random draw. These 2 random coefficients, R1 and R2, are what make PSO stochastic. Run it twice from the same starting point, and you'll get slightly different paths. Here's our particle at position X sub I. The cross marks its personal best. The gold star is the global best. The inertia component, blue arrow, is just the current velocity direction, scaled down by W. The cognitive component, purple arrow, points from the particle toward its personal best. The dashed line shows the full distance. The arrow is a fraction of that, scaled by C1R1. The social component, gold arrow, points toward the global best. Same idea, a fraction of the full distance, scaled by C2R2. Add all three vectors. That's the new velocity, not where the particle goes, where it will go. The position update is one more step, and that's what we'll cover next. After all that, the position update is almost anticlimactic. New position equals old position plus new velocity. That's it, you've already done the hard work computing the velocity. The position update is a single vector addition. Green is where you're going, blue is where you are, purple is the velocity that bridges them. Here's the particle at its current position. Here's the velocity vector we just computed. The sum of all three forces. The particle moves by exactly that vector. New position, new evaluation, new potential personal best. And then the whole cycle repeats. Velocity update, position update, evaluate, compare, repeat for every particle, every iteration. There's something worth sitting with here. The velocity equation is where all the intelligence lives. The position update is just arithmetic. PSO concentrates its entire decision-making into that one equation, inertia, memory, social influence, and then executes it mechanically. That's the elegance of the algorithm. Complex adaptive behavior from simple repeated arithmetic. Before we throw the full 2D swarm at you, let's strip the problem down to one dimension. Same algorithm. Same three forces, but now the search space is just a line, and we can watch exactly what's happening. This is the Rastrigan function in one dimension. A classic stress test for optimization algorithms. The x squared part gives it a bowl shape overall, but the cosine term corrupts that bowl with regular, evenly spaced local traps. From above, it looks almost periodic, almost predictable. And that's exactly what makes it dangerous. A gradient-based method will fall into whichever valley it starts near and stop there, convinced it's found the answer. These are the local minima, multiple valleys all claiming to be the bottom. The true global minimum is at x equals 0, where fx equals -10. Every other valley is a dead end, 5 particles, scattered randomly along the x-axis. Each one sits on the number line, not on the curve itself. We are searching for the x value that minimizes f, so the particles live in the input space, not the output space. The purple markers below each particle show their personal best, the best x position each one has individually visited so far. At initialization, that's just wherever they started. The gold star marks the global best, the single best position found by anyone in the swarm so far. Let's run the first 5 iterations slowly. Watch the particles, watch the personal best markers shift, watch the gold star migrate. Notice what's happening. The particles aren't moving randomly. They're being pulled toward their own best positions, toward the gold star, and carrying some momentum from their previous direction. Some particles are converging quickly. Others are still exploring the outer regions. That diversity is the point. The swarm isn't betting everything on one location. Every time a particle finds a better position than its personal best, that marker updates. Every time a personal best beats the global best, the gold star jumps. Now let's let it run. Watch the gold star, watch where the swarm clusters. Converged. The swarm found the global minimum at x equals -1. And here's what's worth noticing. No single particle knew where the answer was. The answer emerged from the collective behavior of 5 agents running a simple update rule for 30 iterations. That was one dimension, one axis, one line to search. The real problems, the ones PSO was built for, live in 2, 10, 100 dimensions. The algorithm is identical. The behavior scales. Let's see what it looks like when we add the second dimension back in. This is the main event. Everything we've built, the 3 forces, the velocity equation, the 1D intuition, all of it comes together here. 20 particles, 2 dimensions, 50 iterations. Let's watch. The landscape is back. Same objective function as before, now shown as a 2D contour map. Each ring is a constant value of f of x, y. The rings get tighter toward the center. That's where the function drops steeply. The gold dot marks the true global minimum at x equals 3.14, y equals 2.72. The swarm doesn't know where that dot is. It has never been told. It's going to find it anyway. 20 particles initialized at random positions across the search space. Each one has a velocity, a personal best, and access to the swarm's global best. That's the complete state of the system, nothing else. Watch the trails, those faint lines behind each particle. They'll tell the story of where the swarm has been. The first few iterations, slowly. Notice the particles aren't all moving the same direction. Some are heading toward the upper left, some toward the lower right. The swarm is genuinely exploring, not collapsing immediately onto a single point. But already you can see structure emerging. Particles that started near the bottom right are being pulled toward that region. The global best is updating. Watch the counter. And as it does, every particle feels a slightly stronger pull in that direction. This is the social influence propagating through the swarm in real time. Full speed now. Watch the trails paint the landscape. The swarm isn't searching randomly. It's intelligently concentrating its search budget. The outer regions get abandoned. The promising regions get denser. Watch the global best value in the corner. Each time it drops, some particle has found a better position than anyone in the swarm has ever found before. That information instantly influences every other particle's next move. This is collective intelligence. No central controller, no shared memory beyond a single coordinate. Just 20 agents running the same arithmetic, communicating one number. Converged. The swarm has clustered around a single region. The trails have converged from 20 independent paths into a tight knot. The global best has stopped updating. There's the answer. The swarm found the global minimum at x equals 3.14, y equals 2.72, within rounding error of the true answer. The function value at that point is close to the theoretical minimum. 20 particles, 50 iterations. No gradient, no calculus, just the three-term velocity equation repeated. And that's what makes PSO genuinely remarkable. A classical optimizer needs the gradient, the slope of the function at every point it visits. For many real-world problems, that gradient doesn't exist. The function isn't differentiable. It's noisy. It comes from a simulation or a physical experiment or a neural network with discrete components. PSO doesn't care. It only needs to evaluate f at a point and get a number back. No derivative, no continuity requirement, no smoothness assumption, just particles, following simple rules, finding answers that calculus can't reach. We've seen PSO work beautifully with W equals 0.7, C1 equals 1.5, C2 equals 1.5. But where do those numbers come from? And what happens when you get them wrong? These three parameters are the only knobs you have, and they matter more than most people realize. 3 runs, same starting positions, same objective function, same random seed. The only difference? The parameters. Left panel, high inertia. W equals 0.9. The particles carry a lot of momentum. Middle panel, balanced. W equals 0.7. The configuration we've been using. Right panel, high social. C2 equals 3.0. The global best exerts 3 times as usual pull. Same problem. 3 very different personalities. All 3 swarms start at identical positions. This is a controlled experiment. We're isolating the effect of the parameters. Nothing else changes. Watch carefully. The left swarm, high inertia, spreads out aggressively. Particles carry their momentum across the landscape, covering ground quickly. They're exploding. But notice how slowly they commit. That momentum that helps them explode also makes it hard for them to stop and refine. The middle swarm, balanced, explodes initially, then begins tightening. The inertia is lower, so when a good region is found, the particles can actually slow down and cluster there. Exploration gives way to exploitation at roughly the right time. The right swarm, high social, is the most dramatic. Watch how fast it collapses. The C2 equals 3.0 means the global best is pulling 3 times harder than usual. The moment any particle finds something decent, the entire swarm is yanked toward it. Fast convergence. But toward what? All 3 are trapped. This is where you have to play around with the parameter values and perform a parameter sweep to see how it affects the optimization process. We've watched the swarm converge. We've tuned the parameters. Now let's slow everything down and do the arithmetic. Precisely, carefully, one step at a time. The full PSO algorithm has 3 phases. Let's write each one down formally. Phase 1, initialization. Every particle gets a starting position drawn uniformly at random from the search space. Every particle gets a starting velocity, also random, centered at 0. At the start, each particle's personal best is just wherever it was initialized. It hasn't been anywhere else yet. And the global best is set to whichever particle happened to start at the best position. The minimum F value across all initial positions. Again, just an accident of initialization. It will change quickly. Phase 2, evaluate and update. For each particle, evaluate the objective function at its current position. That gives you Fi. If Fi is better than this particle's personal best, update P best. The particle has found a new personal record. If that new personal best is better than the global best, update G best. The whole swarm just learned something. These 2 conditional updates are the entire memory mechanism of PSO. 2 comparisons, 2 assignments. That's it. Phase 3, move. The velocity equation, which we've now seen several times, updates each particle's direction and speed. Inertia, cognitive, social. 3 terms, color-coded here. Blue for inertia, purple for cognitive, gold for social. Then the position update, x gets incremented by the new velocity. The particle physically moves. Repeat phases 2 and 3 for every particle, every iteration until convergence. That's the complete algorithm. 3 phases, 2 equations, 1 loop. Abstract equations are necessary, but let's make them concrete. Thank you so much for watching. I hope this helps you understand the particle swarm optimization algorithm in an easy manner.